Welcome back, everyone. So today what I want to do is go ahead and finish up on the binary weighted resistor digital to analog converter. We'll see one more digital to analog converter, and then I'll go over the analog to digital converter. And you'll find that the two actually work kind of the same way, but in reverse. So let's go ahead and let's see that binary weighted resistor DAC one more time. And remember, the idea here is we are taking some number of digital inputs, either 0 or 5 volts for each one of these wires, and turning it into an analog value on the range of 0 to our Vref. So in our case, that's going to be 0 volts to 5 volts, all values in between. And our digital inputs can either take on a value of 0 or 1. So I'll use, I'll use B0, B1, B2, and B3 to represent our binary inputs, and our output we'll just call V out. Okay, and of course the way we constructed this, as we discussed last time, let's go ahead and write that up. And I'll keep it in this order where VB3 is our most significant, VB2, VB1, and VB0 is our least significant bit. Where's my whiteout? Now, like I showed with LT Spice last time, you're taking the weighted sum of whatever the bit is that is applied here. So if we had, let's say, 5 volts for B0, that only contributes the higher resistance, where our most significant bit contributes the least significant, the smallest resistance value. So if you think about it, what we've done is we've taken our resistances here, R and 2R. So if this was 100 ohms, 200 ohms, 400 ohms, and 800 ohms. And so the smaller resistance is going to have the bigger contribution to the voltage on the output. And so our most significant bit, which will have the biggest contribution, gets the smallest resistance. And I showed this last time with LT Spice. If I went ahead and jumped back to that LT Spice model, I just have a counter set up here at the bottom in order to simulate the values applied to the binary weighted resistor digital to analog converter. And if you've noticed here, I've picked my values such that we have for R, it's 1K. For 2R, we have 2K. So R is 1K, and for 4R we have 4K, and for 8R we have 8K. And if I go ahead and simulate and run this, you can see if I, let's see, kill the R2R pane there, and if I zoom in a little bit, you can see that we get this staircase pattern. Okay, so these are all possible analog values that are being output from our binary weighted resistor DAC. And you can see the stimulated binary values that we're applying to the input of this DAC. Okay, and if you notice, we start off at 0 and we go all the way up to 5 volts. Now, the easiest way to analyze this circuit is actually by using Millman's theorem. Now, I don't have enough time in this class in order to derive Millman's theorem, but I do have a video of doing it under the 211 page, as that's something that I added over there. So if you are interested in how you arrive at Millman's theorem, you can always check out that video. But let me go ahead and just give you the result of Millman's theorem, and then we can go ahead and apply it for the case of analyzing the binary weighted resistor DAC. Okay, so in general, Millman's theorem let's call this R1. And we have a voltage VB1, and so Millman's theorem is about solving a bunch of parallel branches where each parallel branch consists of a voltage source in series with a resistance. And so we could have as many of these as we want, but we're going to end up with a series here of R1 all the way up to Rn, and VB1, VB2, VB3, all the way up to VBN. Okay, and then if you think about over here as this being our V out, and this over here would be our ground, or you can just think of V out as being the voltage between these two terminals. The result that you get from Millman's theorem is that V out ends up being equal to VB1 over R1 plus VB2 over R2 plus VB3 over R3 plus dot 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 VBN over Rn. And now all of this gets divided by the sum of the inverse of the resistances. So 1 over R1 plus 1 over R2 plus 1 over R3 plus dot 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 1 over Rn. Deriving this is actually not terribly difficult. You can do it using only your 211 materials. What you end up doing is You do a source transformation on each one of these voltages, and then you solve for the Norton equivalent circuit of it, and you end up getting this equation. Like I said, I have a 211 video on the actual derivation of Millman's theorem, and the result ends up looking like this. Now, Millman's theorem ends up being probably the easiest way to go ahead and analyze our binary weighted resistor DAC, and I'll show you why. Here's what we had before for our binary weighted resistor DAC. And if you think about it, what I have here is a voltage. So VB3 is a voltage source, and it's in series with this resistor, and V out is here. So actually we can just kind of take this and turn this around. So what I'm going to do here is let's take VB3. So let me start with actually with VB0. I'm going to take VB0, and keep in mind this is a binary, this is a digital value. So VB0 is either going to be 0 volts or it's going to be 5 volts. That's supposed to be 2R. And 2R is associated with VB2. So all I've done is gone ahead and taken how I previously wrote the binary weighted resistor DAC and turned it into something that very much looks like what you would get from Millman's theorem, right? It is essentially the same thing. And so now you can go ahead and you can express your binary weighted resistor DAC as a V out in terms of the voltages and the resistances. Now, what you get once you plug that in, and I'll abbreviate binary weighted resistor DAC. And I'll give you the general equation, which is going to be V out is equal to 1 over 2 to the n minus 1. Keep in mind n would refer to the number of bits that you have, or your resolution of the DAC, times 2n minus 1 times VB0 plus 2n minus 2 times VB1 plus 2n minus 3 VB2 and all the way till you get to your least significant bit, which will be 2 to the 0, or 1 times VBN. Okay, so here's what you end up getting for a generalized equation for the binary weighted resistor DAC, given that you've gone ahead and solved it using Millman's theorem, where we converted it into a form like this. Now, if I go ahead and do this for something a little easier to solve on paper as opposed to a 4-bit, if we did it for, say, a 3-bit, we would end up with this equation for V out, where since you have 3 bits, it's going to be 2 to the 3 minus 1, or 1 divided by 7, times 4 VB0 plus 2 VB1 plus VB3. And I've just given some test inputs here where I went with our lowest value that we could have for our digital inputs, which is 0, 0, 0. And we should get 0 volts coming out of this digital to analog converter, so it's going to turn these zeros into 0 volts. And of course, if you plug that into the equation, you end up with 0. And then I looked at it at the max case of the largest value you could get for a 3-bit digital to analog converter. That would be all ones in the inputs, so 1, 1, 1. We would expect to get 5 volts out of that, and sure enough, when you plug it into the equation, you get 1 divided by 7 times 4 times 5 plus 2 times 5 plus 5, and you end up with 5 volts. And then I took the halfway case, where we're giving it 1, 0, 0 over here, and you might expect, you would think that you're going to get half of the voltage, 2.5 volts out, but as you see, it's actually not exactly at the halfway. When you go ahead and solve that out, you get 2.857 on that. Okay, and if you were to do it for a 4-bit, kind of the same thing. Notice now we have that extra most significant bit here, and 2 to the 4, 16, and 16 minus 1. So you end up getting this equation, and if we were to give it all these different values, we'd end up getting, again, I looked at the min case 0, the max case 5 volts. I did the midway point here, we get 2.66, and I just took another just random point to go ahead and solve for, and you get 3.33. Of course, this is the same 4-bit DAC that I showed previously, and this is probably an easier way to visualize it, as we get all of our values going from 0 volts all the way up to 5 volts. So very easy way to get a digital to analog converter. It does have some drawbacks. Okay, some drawbacks and some problems associated with this is the larger you go in resolution, the harder it is to get those values. If you think about it, those resistances are scaling by a power of 2. And so even if I jump back over to the circuit, 1K, 2K, 4K, 8K. This is easy to do. What happens when you go to 5 bits? Well, now you need a 16K. What happens when you go to 6 bits? You need a 32K, a 64K. So the difference between the smallest resistance and the largest resistance starts getting completely out of hand. So a binary weighted resistor DAC, it's clever, it's nice, and it's simple to work with, but it has some very practical limitations, which is you just can't get up to large n-bit digital to analog converters because the resistances start going way out of hand. The other problem is, if you've noticed in your resistor kits, you don't have a 1K, well, you do have a 1K, you may have a 2K, you probably don't have a 4K, 8K might be unobtainium, 16K. Finding those precise values is just a difficult thing to do, and you need, if you're making an 8-bit digital to analog converter, you're going to need 8 very specific values. Good luck finding all those values. Now, you could go ahead and construct those values out of, other smaller resistors, and I can take 2 and put them in series, or put that in parallel with something else to try and get that precise resistance value that you need to make this work. But generally speaking, that's not very practical if you're trying to make a product. The other problem that you're going to have, you need precision resistors. If you think about your resistance precision being off by 1% or 2% on any one of those values, especially when you get to larger n-bit digital to analog converters, it starts becoming a bit problematic. So again, that's another limitation. You need precise resistances. It's not easy to maintain those resistance values of those powers of 2, and trying to find them and buy them is going to be difficult at best and very expensive even if you could, and especially if you needed them to be very precision resistors for a larger DAC. So those are 2 very real practical limitations of a binary weighted resistor DAC. And then there's this other one. Different currents need different wattage ratings. Yeah, if you think about it over here, R1 has more current going through it than R4 does, right? It's a smaller resistance. Resistance and current are inversely proportional. If I keep the voltage the same, just look at Ohm's law. So over here, this is going to have to be a much larger watt rated or larger power rated resistor than our 8K is. Probably that one isn't as much of a problem because you can just set it up so you have very little current, but it is a pain in the butt. Okay, so if I'm talking about all of these problems with a binary weighted resistor DAC, then I must also, or at least I should, offer an alternative that is better. I will. Give me a second to find the slide. Here we go. Okay, better than a binary weighted resistor DAC is going to be an R2R ladder DAC. And the general form of the R2R ladder digital analog converter would look like this. Let's take B0. So I'm going to start with my least significant bit over here. And I'm going to have my inputs labeled at top on the top because it's just the easiest to draw it. R. R2R, and ground over here. Okay, so what did we do here? Okay, we created kind of a voltage divider over here. And we get V out, and you can extend this for as many bits as you want. You just keep on adding these legs over here, and you can get a B4, a B5, a B6, depending on the resolution that you would like from your digital to analog converter. Now, if you've noticed, we've kind of gotten away from the problems that we talked about for the binary weighted resistor DAC. You know, one of the problems was those hard to get values. Well, now everything is just in terms of one resistor or 2 times that resistor. So if all I have are 1Ks and 2Ks, it's very easy to create this R2R ladder digital analog converter. You know, 2K here, 1K, 2K, 1K, 2K, 1K, 2K. If I want to scale this up to 16 bits, no problem. 2K, 1K is all day long across the board. So this design for a digital analog converter is much more practical, and you will find this in many products wherever you need a very cheap yet fast digital to analog converter. By fast, I mean how long does it take to get that output voltage to settle at your desired output. Now, I've also done an R2R ladder DAC in my LT Spice simulation. And I did a 4-bit over here as well. And notice the same thing over here, ground on one side, my least significant bit here, a 2K, 2K, 1K, 2K, 1K, 2K, 1K, 2K, and so forth. And then I get my voltage out from the DAC. And if I go ahead and simulate and run this, now let me go ahead and add that VDAC back. Probe the voltage there. There we go. Okay. And now you can see essentially we are getting the same thing as the output from this DAC. There is one little drawback. The R2R ladder DAC is not all sunshine. You don't reach the full scale value, so even though our VREF is 5 volts, you can't actually get to your highest voltage. Up here, it's a little hard to see. Let me see if I can cut out, let's do this. Delete my B3 and delete my B2. Okay, a little easier to see. So up here is 5 volts. We don't actually reach our full scale value of 5 volts, where with our binary weighted resistor DAC, we do. Now that can be seen as a disadvantage, but so what? So what? We don't reach our full scale value of 5 volts out. Might not be the end of the world. In fact, most of the time, It isn't. And even if it was, you could actually just compensate for that by having a little amplifier at the very end. So, you're solving a lot of problems and you're just getting a little annoyance for the sake of going with an R2R. So an R2R ladder DAC ends up being the preferred one for most practical designs and solutions that are out there. And now, is this just an academic thing? No, it's the complete opposite. This is a very useful thing. Being able to convert digital values to analog values is so incredibly valuable. And a good example of this specific R2R ladder DAC, I have one in my function generator. I took my function generator apart, what I've been using to apply my analog signals to, any circuit that I've done a demonstration on. And if you open that up, it has an R2R ladder DAC in there. And it's a pretty, versatile, useful design. And practically speaking, it's very easy, it's very cost effective, and it doesn't suffer from that many problems. And like I said, this output of not reaching that 5 volts out, no big deal. You can just compensate for that with a little, amplifier at the end of the day on the output using an op amp, and your problem goes away. Now, as far as solving the R2R ladder, I am not gonna have time to do this. I'll quickly put up a slide. So let me go ahead and put up this slide. And this is not, again, this is not something I'm going to hold you guys to on an exam anyways. But can you go ahead and derive this given things that you already know? Yeah, absolutely. This is a 2-bit R2R ladder circuit. For the sake of being able to derive it, I went ahead and kept it simple. And what could be simpler than a 2-bit digital to analog converter? You only have 4 different values that you could have on the output. And so you can do it using a combination of Thevenin and superposition. If you go ahead and take our 2-bit R2R ladder circuit, and if I rearrange it like this, VB0, and then you solve for the voltage between A and B, and then you go ahead and plug this back into your original and then apply superposition. Okay, you're going to end up with a result like this where we have half of the voltage contributed by B1 and a quarter of the voltage contributed by B0. That's for a 2-bit, and if you have a 3-bit or higher bit, then you start to get higher fractions, so you get less and less contribution by each of the bits as you get progressively closer to that least significant bit. So it is not a difficult thing to derive or solve for. And in general, I did come up with 2 solutions. This might be a little harder to see. This was the result of my derivation for a 3-bit DAC I came up with this, and then I tried to find the more formal formula for V out, and it ends up being the exact same. So that's always good. Not a good day if your derivation of something ends up giving you a different answer. Okay, and then what I did over here was I also put some, I did a 2-bit truth table essentially for the V out for my R2R ladder, the 2-bit version of it, and you can see the 4 different values that we would get for V out. 0, 1.25, 2.5, 3.75, and notice that the full scale output does not go all the way up to 5 volts. You just can't do that with an R2R design. But as I said earlier, it's not that big of a hindrance. Okay. So 2 different circuits essentially do the same thing. One is much more practical in the real world. And then what I did was I constructed these. And over here, I have done a binary weighted resistor DAC on the left side, and I used 4 bits from one of my ports from this 8051. And I've written the values out here on the side, and so you can see the 2K, 4K, 8K, 16K, and for the R2R ladder DAC, I've done the same thing, labeling it here. We have our 2K and 2K. Yeah, both of these together are 2K connected to ground. We have our least significant bit over here. 1K, 2K, 1K, 2K, 1K, 2K in that ladder arrangement. I do have this actually going the opposite direction of what the paper wrote, just because it was easier to lay it out this way. I had it where the most significant bit was on the right on this board where I soldered it. The most significant bits on the left. And if I go ahead and pull up my oscilloscope, we can see the result of both of these actually at the same time, because I'm writing the same value to each one of them. So let me go ahead and let me program that up. Give me a second to get this started. Okay, there it is. And let me pull up the oscilloscope. Probably helps if I have it connected. There we go. And I'm going to set these for the same scale. Okay, much better. I'm not sure what that was. Okay. Now, right now, the yellow is connected to the yellow signal of interest is connected to the binary weighted resistor DAC. And keep in mind, this is a 4-bit DAC, so we have all of 16 values that we can output from this DAC. And then the R2R ladder is the same thing. It's a 4-bit DAC, and he is on the blue signal. And if I go back to the waveform, you can see over here with them superimposed, the binary weighted resistor DAC reaches that full scale value. Whereas the blue one, or the R2R, does not. They are doing virtually the same exact function, which is taking the same digital output and outputting it as an analog voltage. And you can see that same staircase pattern identically from the LT Spice simulation. And if I move one of these, they are covering each other up in the beginning of the bits because they're very close to each other till the very end. But you can see that they're essentially the same. Okay, now let's see. Do I have any questions about this thus far? If there's any questions about this, let me know in chat. Okay, so hopefully pretty straightforward. Now, I did do one thing for fun with both of these DACs because, you know, staircase pattern's not that fun. Let me go ahead and switch this over. Every oscilloscope has the ability to show what's called XY mode, where it uses one channel to change the point on the screen at the x-axis, and then the channel 2 is tied to the y-axis. And so you can actually draw pictures on any oscilloscope with this XY mode, which is kind of cool. So if I go overhead, switch my switch my acquire mode to XY, we can actually display the x-axis in relationship to the y-axis and can even draw images on it. Now I'm going to have to change to a different program here. I would have configured this up as the fun mode button, but I haven't had time to finish this yet. Of course, why would it work? I'm going to have to disconnect. And reconnect. And download. And run. That looks terrible. Let's see. Okay, that's a little better. Okay, it's a bit hard to see. It does or is supposed to say ENGR at the top and my name at the bottom, ERIC. Now, one of the drawbacks to a digital storage oscilloscope is, which is what I'm using right now because that's the easiest to connect, is that they do have terrible XY modes. Their XY modes just don't look that great. And it's because it's easier to do this when you have an actual cathode ray tube like an old school TV. So hopefully at least the point is getting across. So what I did over here was I took each one of my my two digital analog converters, and for each point that's being displayed on the XY plot, I'm outputting my desired values. So I really only have 16 values across the y-axis and 16 values across the x-axis. So there's only so many places where I can draw a point on the screen, and then I have to move that point to the next point. So it's kind of like drawing with a light, old school light bright, or maybe like an Etch-a-Sketch. But nevertheless, okay. So that I think finishes up the DAC. Now, what I want to do is cover the analog digital converter. So we're going to go in the opposite direction now. And I'm going to go ahead and use a little bit of lab time for this. So why don't you guys take a 10-minute break here, and I will start back up at 9:05, okay? Start recording again. As well as converting a digital value into an analog value, we can do the same thing in reverse. We can take an analog value and measure it and turn it into a digital value. So think of this as converting an analog voltage into a numeric value. Okay, and this is called an ADC, an analog to digital converter. And all the same things that we said about a digital to analog converter is applicable to this. So we have some analog voltage coming in, and we need to specify the range. So we're going to have a VREF as well. So let's just go ahead for the sake of example. All of my examples are going to use a VREF of 5 volts, just like I did with the digital to analog converters. So our VREF is 5 volts, and so that'll mean our VIN is going to be 0 volts to 5 volts and all values in between. And then we need to go ahead and specify the resolution. Okay, and so if we had, and for my examples, I'm going to use a 4-bit analog digital converter. Then we're going to go ahead and have 4 wires coming out of this, 1 to represent each bit, and each bit can take on a state of 0 volts or 5 volts. Now, once you go ahead and specify the resolution, we can calculate the step size. So the step size that we talked about in regards to the digital to analog converter is also applicable in this case as well. So the step size is going to be equal to your VREF divided by the number of steps, or the number of values that you would be converting it into. Since we have 4 bits, we have 2 to the 4. Or in our case, for a 4-bit analog digital converter, we can go ahead and take our VREF 5 volts and divide it by 2 to the 4, or 16. And when we do that, you're going to get a step size of 0.3125. And so if I had a value here, and let's just go ahead and say that in this example, our VIN is going to be 1.6 volts. And with a VIN of 1.6 volts, just for example, what value numerically would that be converted to in a digital output over here from our analog digital converter? Well, to do that, we just take our VIN and divide that by your step size. So in this case, we're going to take 1.6 volts and divide it by 0.3125. Now, you're not going to get you're not going to be able to get a fractional output here because it is a discrete digital value that you're going to get on the output, but we can go ahead and just round that to 5. Okay, so a value of 1.6 volts gets converted to a numerical value of 5 on the output. And remember, our output for a 4-bit ADC can only be 0 to 15, because you only have 4 bits to represent whatever analog voltage you have here on the input. Okay, now there are a few different ways to construct an analog digital converter. Namely, there's a flash type, or it's called a flash topology for our analog digital converter. And there's also another one which I will cover, which is the successive approximation technique. The successive approximation technique, or the successive approximation topology for constructing an analog digital converter, well, we call it a SAR ADC. And we're going to have to put a few things together in order to construct our ADC. Or our analog digital converter. Okay, now first up, what we're going to have here is a sample and hold. And all that the sample and hold is going to do is take whatever analog voltage we have here on the input, and it's going to hold it in here so that as Vin possibly changes, we are still going to be converting on the same value. So when you think of a digital to analog converter, the two that we saw thus far, the binary weighted resistor and the R2R ladder, are both very much like, to draw an analogy, it's very similar to our combinational circuit, for a digital combinatorial circuit. The output is always a product of your current inputs. There is no state associated with it. But when we do an analog digital converter, we actually are going to do a process. We're going to do this iterative process to convert our analog voltage into our digital values on the output. Okay, and so since it's going to take some time to do this, we don't want our Vin to change on us as Vin is going up and down and changing voltage on us. So that's the reason for having this sample and hold over here. Now, what are we going to do with that value once we've sampled and held it? We're going to do a comparison on it. Looks familiar, right? So an op amp, you could use an op amp with no feedback, and you can create yourself a comparator out of this, right? We have that very high intrinsic gain associated with the op amp. We called that the open loop gain. And this comparator is just going to tell us which voltage is higher. The value from V in, so, you know, the sample and hold here is for a practical implementation of this, but you could just think of the voltage here as being just V in, as long as V in is static and doesn't change. And we're going to compare that to some other voltage. What are we going to compare that voltage to? We're going to compare it to the output from a digital to analog converter. So I'm going to go ahead and call the voltage that we're comparing V into, I'm going to call that VDAC. And so what we're going to do is we are going to take whatever analog value that we have coming in, and we're going to test it against changing values of our digital analog converter. So over here, we're going to feed this some digital values, and we're going to get some voltage coming out of our DAC, and we're going to compare that to our incoming voltage, and we're going to search for which is the closest one, hence successive approximation. You can kind of think about this as like a binomial approximation. So we're going to be trying to find which is the closest value. So if we're at 1.6 volts, we're going to go ahead and go at the halfway point. Is it above or below? Okay, it's below, so we're going to go ahead and go halfway in the other direction. Are we above, below? Okay, we're below. We're going to go ahead and go halfway in the other direction, and we're going to eventually search and find what the closest digital to analog conversion is to our V in, and that will be the result of our ADC. So you can think of this as an iterative process to find what the analog voltage is in regards to a digital value. And this is the most common topology and implementation for an analog digital converter. You're going to see these in 346, 347, 447. They're built into our microcontrollers, and I can tell you they all use this topology to do that. There are other types of analog digital converters, but for some practical reasons, this ends up being the best compromise of cost to performance, to easeability of construction, and speed. These are actually pretty decent all around analog digital converter types. Now, I'm going to have to put some values here, and we'll step through the whole process of doing an SAR conversion. Okay, now for my V in, I'm going to use the same V in that I used earlier. I'm going to say it's 1.6 volts. And since I'm going to not want to spend all day here performing this conversion, I'm going to assume a 4-bit analog digital converter. With a 4-bit analog digital converter, hopefully it's not a surprise, we're going to use a 4-bit DAC. And that means we have 4 digital wires feeding the input to this DAC. And our step size for this, well, let's go ahead and establish what our Vref is going to be. Vref is going to be equal to 5 volts, because I'm going to use 0 to 5. Keep it consistent with everything else we've previously covered. And so our step size is going to be equal to our Vref, which is 5 volts, divided by 2 to the 4, because we can represent 16 discrete values with this 4-bit analog digital converter. And so our step size is going to be 0.3125 as we calculated earlier. Okay, and what I'm going to do is I'm going to set up a table here for each iteration of this SAR process as we convert our analog voltage to our digital voltage, or our digital value that we want coming out of here. So what I'm going to do is I'm going to list the value being output to the DAC. So this value over here, let's call this DAC in. And then the output from the DAC is going to be VDAC, so I'll list this as VDAC. And then I will put the result of the comparison in the next column. Comparison. And then we'll look at the bits in the rightmost column. Okay, so let's go ahead and let's start off this SAR process. First thing we do, sample and hold. We take this value and we fix it so that if this changes, it doesn't change over here while we are taking measurements of it. So Vn is going to be equal to 1.6 volts. Now we're going to have to go ahead and give the DAC some input so that we have a voltage that's being compared to the 1.6 volts. Now, for our purposes, you're going to always pick the halfway point. The halfway point would be 1, 0, 0, 0. So what we're doing is we're setting the most significant bit here, leaving all other bits 0. Okay, so that's going to give us the halfway point with our most significant bit being set to 1. Now, what's going to be the output from VDAC? Well, to do that calculation, you're just going to take the numerical digital value that's being fed into it and multiply it by the step size of our digital to analog converter. So over here, we're going to get 8. Since 1000 is 8, and it's going to be 8 times our step size. Our step size is 0.3125. So the output from VDAC is going to be 2.5 volts. Now, one thing you may have noticed already, which is I put up 3 different ways to calculate this value coming out from VDAC. In one case, the first general sense, I showed just take the step size and multiply that by whatever numeric value you have coming into it. And this is totally acceptable to do. But then I also put up an equation for V out for the binary weighted resistor DAC, and I put a V out for the R2R ladder DAC, and all 3 of those values are slightly different from each other. Okay, so it is dependent on what type of DAC you're going to place here. And I did say that the R2R is the more practical one. That being said, I'm not going to focus that much on the nuances between a binary weighted resistor, an R2R ladder DAC, there's sigma delta DACs, there's all sorts of different types. So apples to oranges. Let's just do the simplest one. Take the step size, which is given by Vref divided by the number of steps, and multiply that by the DAC input. Okay, this is going to be the simplest way to calculate it. Is it as accurate as if, was I constructing this with an R2R? Maybe I was. If you want to be more precise, by all means, you can go ahead and use the equation that I gave for an R2R ladder DAC, and you can calculate it that way. But the step size, this will be the easiest way to do it. Okay, so now we know we have 2.5 volts coming out of this DAC. Well, 2.5 compared to 1.6 volts. So now what we're going to do is we're going to check what the output of this comparison is. And we're going to make a decision based off of that. Okay, the result of this comparison, we are comparing 2.5 volts to 1.6 volts. We want to know, is V in less than or is V in greater than? Well, as it turns out, VDAC is greater than V in. If VDAC is greater than V in, you're going to clear this bit. And that means our most significant bit is actually 0. Okay, so we set it to 1 initially. We compared it to our input voltage. Turns out VDAC was greater than VIN. If it's greater than VIN, you just go ahead and clear that bit. So this 1 now goes to 0. Okay, now what do? Set the next most significant bit. All other bits remain 0. Okay, so this is going to be the result of our first iteration, and we're going to go through 4 iterations for a 4-bit successive approximation analog digital converter. Now, if we go ahead and look at this as a graph, over here, I've listed our VDAC along the x-axis, along the y-axis, and across the x-axis, I'm putting time as we successively approach our actual VIN. So our VIN is 1.6, and I've drawn this as a black line going across the whole graph, and then I've broken it up for each iteration. So right now, after the result of our first iteration, this is where we're at. We set VDAC to be 2.5 volts. So we did 1000 as an input into our DAC, and the output that was being compared was 2.5 volts to 1.6 volts. We found that it was higher, and so that told us we need to clear that bit. And so we did. We cleared that most significant bit, and now we're going to go ahead and set our next most significant bit. So now we're going to go ahead, take our DAC input, and let's compute what the output from the DAC is going to be. Let's compute what VDAC is. Well, that's going to be easy. Our input is now numerically 4, so we're going to do 4 times our step size. What's that equal to? It's going to be equal to 1.25 volts. Okay, so now we're going to be comparing 1.25 volts to 1.6 volts. Is VDAC greater than 1.6 or is it less than 1.6? It's less than 1.6. So now you can see the result of the conversion is actually the result of the comparison is actually now the opposite. So VDAC is now less than VN. If it's less than VN, we're going to leave the bit set. You can say no change or set bit, however you want to think about that. I'm going to go with no change. So bit 2 is going to be equal to 1. Okay, so we're going to leave this bit set to 1. So thus far we have 0, 1, and now we're going to again set the next most significant bit. And all lesser significant bits will be cleared. Will stay as 0. Okay, so now as far as this graph goes, we're about here. We initially had the most significant to 1. We found that that was greater than 1.6, so we went ahead and we cleared that one, and we set the next most significant bit, and that left us at 1.25 volts. We found that 1.25 volts was less than 1.6 volts for V in, and so we left it set, and then we set the next most significant bit. So now that puts us at the halfway point between 1.25 volts and 2.5 volts. And we're going to compare that again. So let's go ahead, let's calculate what VDAC is now. VDAC, well, this is 0, 1, 1, 0. That's 6. 6 times 0.3125 is going to be equal to 1.875 volts. And now we're going to be comparing 1.875 volts to 1.6 volts. 1.875 volts is greater than 1.6 volts. So we're going to clear that bit. So bit 1 is now equal to, well, we just cleared it, so it's 0. Okay, so now we're going on to the last iteration. We're going to go ahead and set the least significant bit over here. So we're at 0, 1. Remember that this bit got cleared, so it is now 0. And we're going to set the least significant bit now. As far as our graph is concerned, we started at 2.5, that was bigger. Then we went to 1.25, that was smaller. So then we went up halfway to 1.875, and that was bigger. And then now we went ahead, cleared that bit, set the least significant bit, and we are at this voltage here. Let's go ahead, calculate what that is. 0.101 is 5. So now we have a numeric 5 times our step size is 0.3125. And that's going to be equal to 1.5625. Okay, again, we're going to go ahead and compare 1.5625 to 1.6. The output of this comparison will tell us what to do. Since it is less than, we're going to do no change. Leave it set. Bit 0, therefore, is going to be equal to 1. And we are done with this conversion. So at the end of the day, this ADC converted the value 1.6 volts to 0.101. And that's the result of our conversion. So, as you can see, the digital analog converter is actually crucial to the construction of an analog digital converter. So it's really just an extension of our DAC for our ADC. And by stepping through this successive approximation, we were able to home in on our analog value that we had coming into the ADC. Now, is it exactly 1.6 volts? No, but we only have 4 bits to work with. So this is the best that this analog digital converter can do for approximating a digital value that is equal to our analog voltage that's coming in. If you want to have more precision, increase the resolution of your ADC, and then you can go ahead and step through this yourself for a 5-bit or a 6-bit. But of course, that's going to end up getting larger and larger and larger. But it is not that bad as far as the conversion's concerned, because for each bit you just have one more iteration, so it's not like it grows in exponential time complexity. This actually just scales linearly, and it's not bad. Any questions about ADCs? Yeah. Okay, great. Yes. All of that we just did was just for converting one value. But as we know, analog values change. So if you think about the sampling rate for a microphone, well, what is it that you're sampling? You're sampling a sound wave. So let's draw a sound wave. Okay, so as far as a complex sine wave is concerned, now this is known as a continuously varying time varying signal. And when you get to the class 463, you're going to be dealing a lot with this. Now, if you just look at a pure sine wave just has one frequency. And so if you were to listen to a 1 kilohertz sine wave, it's just going to sound like one pitch, one frequency. You know, right? Now, in human speech, in sound, you have many different frequency components of a more complex, continuously time varying signal. And if I want to put this into memory, well, we know that the result of an analog digital converter is just going to be one value. Great. I can't do much with one value. I need more values, and I need them to be stored in memory. So I'm going to take a sample here. I'm going to take a sample here, and a sample here, and a sample here, and a sample here, and a sample here. Blah, blah, blah. Just keep going, taking samples over and over again. Each one of these is a numeric value in memory. So maybe this first one is 1 and 3 and 5, and then it starts to go back down, 3, 2, and then -1, and so forth. Whatever it is that you've gone ahead, like maybe all of these are above center are positive, and all of them below center are negative. It depends on your VREF and your setup for your analog digital converter, etc. So each one of these turns into a discrete value. And so that's the process of digitization. Also known as quantization. 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 Okay, so you're going to be converting a moment in time to a numeric value and store that in memory. And so, okay, great. But do I do this? Do I have many points, or do I just have a few points? In other words, for two of the same, this is your sampling rate, right? Am I taking do I have a small sampling? Well, I guess this would be a high sampling rate, I guess. Or a low sampling rate. Now, the problem is that as far as putting this into memory, well, if I have too low of a sampling rate, I'm losing this waveform, because look at where I took these samples. If I extend this, let's go with a low sampling rate. And this is a real problem, by the way. Okay, so I sample here, 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 and so forth. Well, what are all those values? Whoa, what are all those values going to end up turning into? So let's go ahead and say, you know, we have, let me use my 4-bit analog digital converter. Why not? And let's say, this ends up, this is full scale up here. This is 0, 0, 0, 0. And over here, I'm going to need something low. Let's say that this is 0, 1, 0, 0. And let's say over here is 1, 1, 0, 0. Let's just do that. Well, what's going to be held in memory is going to be 1, 1, 0, 0, 1, 1, 0, 0, then 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, because I'm only taking measurements at these points, right? This is with a low sampling rate. What just happened? I just lost my sine wave. Like, this isn't a sine wave. This is a square wave. Right? Because I'm at 1, 1, 0, 0, 1, 1, 0, 0. Then I'm down at 0, 1, 0, 0, 0, 1, 0, 0. Then I'm back up at 1, 1, 0, 0. So quantization or digitization of a waveform is prone to, well, losing data for sure, but also just not faithfully recreating your original sine wave. So this turns into, there's lots of issues associated with this, and this is a big area of conversation in computing. And you know, it is better left for 463, and it's better left for, well, having some more experience with analog digital converters. I just went over the very basics of you know, how you construct these two basic building blocks, but they do extend themselves and have lots of issues with them. And I'll give you one really good example of this. Okay, and I want to make sure everyone's still with me. Who has been on the freeway and looked at the tires of the car next to you and it looks like they're going backwards. Who has been driving on the freeway and you look at the tires of that car and it looks like they're rotating backwards? It's like, but it's going forwards, right? You know it's going forwards because you're going forwards and he's kind of sticking with you. But you look at those tires and sure enough, they're going backwards. And the same thing when you look at like helicopter blades. They go really fast and sometimes they look like they're going backwards. What's going on with that? Your eyes have a sampling rate. This is the best illustration I can give of this problem. So you look at the tire, and it looks like this. And then you look at the tire again. However, it's moving much faster than your eyes can measure. So the next time that your eyes take a snapshot of that tire, it's done almost one full revolution. It hasn't done one full revolution, it's done almost one full revolution. And then your eyes take another picture. Again, that tire is going at a certain rotational velocity where it has almost done one full rotation, but not quite one full rotation. The next time your eyes take a picture, it's now over here. Again, it's going to do almost one full rotation, but not quite. You see where I'm going with this, right? Yeah, somebody just called it in chat. I'm going to overclock my eyeballs. And when you figure out how to do that, you let me know. Okay, so as it turns out, our eyes just, they can't see an infinite number of frames per second. Now, if you're a bird, you get a few more. Like an eagle or a falcon, you get better eye vision. I don't know what the sampling rate is for a falcon or a hawk. And I think, what's our frames per second that our eyeballs can see? But what just happened here? Well, it looks like, the tire did this. Looks like it's going backwards, but it's not. It's just an artifact of our incredibly slow eyesight. That's our sampling rate for our eyeballs. When this happens, we call it aliasing. And you can kind of think about it. I'm going to need a few more samples. The same thing can happen when you take a measurement, especially of a time-varying signal. I take a measurement here. The next moment in time, I take a measurement here. The next moment in time, I take a measurement here. Next moment in time, I take a measurement here. And so forth. Well, if I take no other measurements and I have a very slow sampling rate for a given high frequency signal, what does this end up looking like when I store it into memory? And in fact, if I keep going, I'm going to get a sine wave because this is going to go down and then it's going to go back up and it's going to go back down. So what I just did was I effectively lost all of my information, and instead I'm representing crap. It's garbage. It's not real. It's not indicative of anything. So this problem is called aliasing. You see it on the freeway when you look at tires. You see it in helicopter blades. You see it in anything that moves faster than your sampling rate can effectively measure. And then you have to answer the question of, well, what is an effective sampling rate? And for that, you get into Nyquist theory, and I will leave that till 463. Now, I could also show this problem on an oscilloscope pretty easily, but I think hopefully I've made the point. It would take me a few minutes to set that up, and I'm not going to put everyone through that. Yeah, these are some really these start getting into real problems that you're going to encounter in future classes and get to. I'm not going to go ahead and get too much into the weeds. I will let you guys know this will be on the final exam. I will ask for an SAR conversion, and I will ask for the VDAC at the different points. It will be for a 4-bit digital to analog converter. It will not be for a 3-bit. It won't be for a 5-bit. I'll tell you right now, it's going to be this same type of example. I may change VREF just to require people to calculate a different step size for the sake of outputting these voltages. But that would be about it. It will be a 4-bit conversion. So what does that leave us with is with the two different types of DACs, the one type of ADC, how to calculate the step size. I will not be asking anything in regards to sampling rate and aliasing, but nevertheless, I think that was good and fun for someone to bring up and for me to talk about, and maybe kind of demystifies life a little bit. I find that the more I learn in engineering, the more the world kind of just makes sense to me. Because when I was a child on the freeway looking out the window and seeing tires rotating backwards, I never had a good explanation of it. I had to become a computer engineer and study Nyquist theory and continuously time varying signals before all of a sudden that made sense. And most people just go through life just going like, hey, I guess the tires just look like they go backwards, and that's good enough of an explanation for me. Okay, the last thing that I want to mention about is to please return the MyDAX latest by the week of finals. Yes, you return them to the same place that you got them. Now, let me go ahead.